So let me just introduce myself. I'm Sayantan, and so this was this talk is going to be about device independent or DI protocols for some important two-party cryptographic primitives. This one being oblivious transfer or OT. This was joint work with my group at the Center for Quantum Technology, like CQT, at the National University of Singapore. So we kind of started this work in 2023, but most of the breakthroughs came after I actually moved to Canada, and this guy Upendra, he moved to Anne Broadbent's group in Ottawa. So yeah. Let's see. So this work is about, as you saw on the title, it's about one of two oblivious transfer OT. So what is this thing? So in one of two OT, you have two parties. You have Alice and Bob, and Alice and Bob don't really trust each other. Okay, and the goal of OT is basically to do the following thing: that you have some sort of interaction, and Alice gets us input from outside, two bits, S0 and S1. So these are bits, okay, and these may come from anything, some distribution, or maybe some other protocol which is calling OT as a subroutine. Bob gets a bit C, but we call it C because it's called the choice bit. Sorry, is there a question? Hello?
I don't think so. No. Yeah. Please continue.
Okay. Yeah. Okay. So Bob gets this bit C called the choice bit, and the idea is that Bob should, at the conclusion of the protocol, Bob should output S of C. So for example, if the choice bit was 0, he should be able to output S0, and conversely, if C is 1, he should be able to output S1. Okay. Now there are some constraints that one has to satisfy to qualify as an OT protocol. So number one is that Alice should have absolutely no knowledge of what C is. And number two is that Bob should not know the bit that is indicated by the complement of the choice bit. So for example, again, if C was 0, he output S0. He's supposed to output S0 for correctness. But he should not know what S1 was. Okay. So for this talk, we are going to basically talk about a variant of OT called RAND OT or random OT. Okay, where this S0 and S1 does not come from outside, and the C also does. C can come from outside, right? But S0 S1 does not come from outside. It's kind of generated as random bits during the protocol. But this is kind of well known that there's a reduction from RAND OT to OT. Okay. So, sorry, from OT to RAND OT, right? So for this talk, we are going to assume that this S0 and S1 are sampled independently and uniformly at random, because essentially the protocol will be generating it internally. Okay. And C can come from any distribution. We'll just denote that distribution by P sub C. So I'm going to, in the next slide, I'm going to make these two conditions slightly more precise, not as precise as possible, but slightly more precise. So we kind of know that when we define security of a certain task, we need some sort of a security parameter. Now, usually, if you read like the standard books, uh, Goldreich and so on, you will find like security parameter lambda or something. But I'm going to make it much more simple here. So, given a security parameter n being an integer, and you can kind of think of n as number of rounds of interaction, or at least the number of rounds of interaction will be some polynomial in n or something like that. Or if you have a quantum protocol, let's say the number of qubits that you're exchanging will be a polynomial of this n. Okay, so given this security parameter n, the first condition is Bob is honest and Alice is the cheating party. Okay, so when Alice is cheating, and we denote a cheating Alice, or like all the registers that a cheating Alice holds at the conclusion of the protocol as Alice star, um, Bob's security will be defined as this: that the joint distribution between Bob's choice bit and whatever else Alice has, like the entire transcript of the protocol, or maybe some sort of quantum state that Alice holds. That is negligibly close, negligible in n, negl close to completely tensor distribution. So basically, the distribution of the choice bit C should be entirely independent of whatever, or effectively independent of what Alice holds. So this condition kind of tells you that whatever Alice has done, she cannot have any information about what the choice bit is. Okay, so this kind of corresponds to this condition, that Alice should have no knowledge of C. The second condition is when Alice is honest, but Bob is a cheating party, and there's a lot to unpack here actually. So what do we want? We want to say that Bob can maybe reveal one bit, but he should not be able to reveal at least one other bit. Okay, but this is kind of not a strong enough condition. Okay, it turns out that, like, people actually played around with this definition quite a lot, and what they came up with is sort of close to this. So this condition is saying that, if Bob is the cheating party, let us consider the joint distribution between Alice's two bits S0, S1, and whatever the cheating Bob star holds. Okay, so this distribution should be decomposable in a convex combination of two other distributions. So let us look at the first distribution. So in the first distribution, notice that the first bit S0 is completely independent, and maybe S1 is correlated to Bob star. We don't really care. But if this is the case, so with probability P, small p, if we are in this world where S0 is kind of intenser to S1 a cheating Bob has absolutely no information about this S0. Okay, and similarly with with probability 1 minus p, in the other world, a cheating Bob maybe has information about S0, but has absolutely no information about S1. So the security condition here is basically that the joint distribution between S0, S1, and Bob star has to be kind of splittable in a convex combination into these two worlds, where in each world Bob does not know at least one bit. Now we don't know what these joint distributions are, like what S1 and Bob star are. Maybe S1 and Bob star are correlated, maybe they're not correlated. We don't really care. As long as Bob doesn't know at least one bit, we're completely fine. And we don't care about correctness when we write this security definition. Okay. Okay. So any questions so far?
Yeah, I wanted to ask a few small things. So,
Yes.
so I remember in commitments, things are a bit more delicate, right? Like you have to look at these collapsing commitments and so on. Do similar things arise in this oblivious transfer as well, or?
Not as much. So one thing that I should state is that this definition that I've written, it's not super precise. Like I say it's slightly more precise, but it's not the most precise definition. Also, this is not the definition that we use in the paper. In the paper, we have a simulator based definition. Okay, and that
Exactly.
is
Yeah.
yeah. Like the thing is, when you're giving a talk, writing the simulator based definition is extremely hard. So
Okay.
I kind of decided to go with this
Okay.
because of some historical reasons, which I'll state shortly.
Okay.
But
So the simulator-based definition would in particular imply this, is what you're saying.
absolutely.
Okay.
The simulator based definition is much stronger than this, and it actually implies like proper security, and the things that you were talking about, like the collapse based issues and so on, or like what even are these registers, Alice star and Bob star? Are they quantum? Are they classical? What exactly is going on here? Those issues are all taken care of in the simulator based definition.
I see.
But
And
for the specific Yes.
Sorry, just while we're still at the topic of simulators, so these are is it UC, like is it universally composable, or is it
Yes,
sequentially
it's UC.
composable?
No. So it's not UC. It's sequentially composable.
Sequentially. Okay, got it. Okay,
In fact, we believe that
it's impossible. UC.
it's impossible because another group at CQT, Marco Tomamichel's group,
Uh-huh.
while we were doing this work, they kind of proved that UC composable weak coin flipping is impossible.
Oh, okay, and then this would imply weak coin flipping in particular. Okay.
Yeah, exactly.
Okay. I see. I see. I see. Okay.
Yeah,
Okay. Thanks.
yeah. No, so like the reason
No,
why
sorry. So
yeah.
these are sorry. Just one last question. These are
No, no,
like
no, no, no.
what kind of security are you looking at? There are no computational bounds, right? These are unbounded because with computational bounds,
Yeah,
of
I'm
course, you
going
can
to,
achieve everything.
yes,
Or
exactly. So I'm going to get to all of those points in the next few slides.
okay. Okay.
Yeah.
Thanks.
So like the reason why I chose to flash this definition will become extremely clear in the next 3 or 4 slides. So this kind of Atul, this slide will kind of start addressing your question. So is this even possible? Okay. So this definition that I showed, this definition assumes no computational bounds, right? Like this is and the kind of security that this gives is called statistical or in information theoretic security. Okay. Um, so it turns out that this answer is actually pretty complicated. Like answering this question is kind of complicated. So it's quite well known that information theoretically secure OT is not possible. Like even if you have quantum resources, even if as in even if you're allowed quantum communication, information theoretically secure OT is impossible. And the proof is actually quite easy. It's just a very simple application of Ullmann's theorem. Um, and this is
Yeah.
very different from sorry.
Sorry, yeah, I had a small question.
Yes, yes.
So, so you said the security definition does not have any computational bounds,
Mm-hmm. Yeah.
but we are just assuming the distributions or like the states to be like negligibly close, right?
Yes, yes.
So if uh, Alice was the dishonest party,
Mm-hmm.
then can't they make use of this negligible closeness? Or by negligible closeness, do you mean like the trace
Great
distance?
question. Yes, exactly. That's exactly what I mean. That the trace distance is negligible. The thing
Okay,
is
okay.
that there's a very good reason why. Like if you open Goldreich's book, you will see that he spends at least 10 pages justifying why negligible closeness in the trace distance, even in the computational secure models,
Right,
is
right,
important because like if two distributions are negligibly close,
Hmm.
that means that no algorithm, like even if you give that algorithm unbounded computational power, that algorithm will
Hmm.
need quite a bit of time to actually distinguish between those two distributions. And by quite a bit of time, I mean one over whatever negligible function this is. So
Right,
even
right.
if you have like 2 power minus log square n, which is a negligible function for large enough n, this is going to blow up very fast. So
Hmm.
that's where this negel closeness business comes in. I mean,
Right, right.
this negel closeness is kind of good enough for us. Does that answer your question?
Yeah. But still there is like this computational constraint that okay, the adversaries can't be exponential.
Yeah, in the computational world, there is such a constraint. For us, we don't like even if for us we don't have that constraint. But as I said, even if you give your adversary unbounded computational power, if you have two distributions which are negligibly close, let's say P and Q, they are negligibly close, and you tell
Mhm.
an all-powerful adversary that you have to distinguish between them, what is the
Mhm.
probability that they succeed? The probability is exactly that if you're sampling for, like let's say you're sampling from P, the probability that you are able to distinguish between P and Q is that you get a sample from P which is kind of a very low probability sample, but on which Q gives a lot of probability, right?
Right.
Now the point is how many such sample points are there? Negligible. Like in probability, there are negligible such samples, as in
Right.
the total weight of probability on those samples which would allow you to distinguish would be negligible.
Right.
So
Right.
it's almost guaranteed that, and so therefore what does that mean? That if you keep on sampling, right, what is the probability that you will hit such a sample? It's exactly the Nagel function. So this is
I
a geometric.
suspect. Just a
Yeah,
quick question. So I suspect you're assuming that you have poly many samples, right, from both distributions. Of course, if you have exponentially many samples, you can do it. But I guess in any real execution, you would only have honest parties, and they would only do
exactly,
poly many samples. So I think that's the key
exactly.
point.
Exactly.
Right.
That's pretty much what we assume. Like even if your adversary has unbounded power, at the end of the day, we want security basically within our lifetimes. Like if we were
Okay.
immortal, then like I would give the adversary a billion years, and sure, like in a billion years, it can maybe sample an exponential number of things. But I really don't care because in a billion years I'll be dead. So right. So yeah, that's pretty much the point behind this negative closeness business.
Yeah.
Hello. Just a quick
Yeah.
thing. No. So in this
Yes.
distinguishing game between the two distributions, is the like probability half, or is it, or do you take it to be half plus negative, or is it like exactly half?
No, there is no half. It's like the one norm between P minus Q is Nagel. If it were like half plus Nagel, then I would be able to distinguish very nicely, right? You're thinking about that half because you're thinking in terms of like distinguishing between the completely uniform coin toss, the toss of a fair coin, and the toss of a fair coin biased by a negligible probability. So the distance between those two distributions is negligible. So you're thinking of this definition that like probability that this algorithm can distinguish is like at least half plus Nagel. No. Like that is equivalent to what I am saying, but in a different sense. Right?
Right.
You understand? So, is that clear?
Yeah. Thank you.
Okay, no problem. Yeah. More questions from this part? Okay. So yeah, so information theoretically secure OT is not really possible, and this is quite this is actually kind of surprising because there are other things which are possible when you have quantum resources which are not classically possible. For example, key expansion like QKD, or rather I should say QKE, but like we have all at least have heard of the BB84 protocol, and BB84 is an unconditionally secure key expansion protocol. So that actually gave people some hope that maybe uh, so like unconditionally secure key expansion classically is impossible. That's very easy to show, but BB84 makes it possible to share secret keys with without like securely without any assumption on the eavesdropper. But in some sense this two-party cryptography business is much harder because here there is no eavesdropper. You're not doing encryption. What you're instead doing is secure multi-party computation, and OT is like the complete problem for secure multi-party computation. So if you can do OT, you can do everything else. And for OT, it turns out that this is impossible. But in 2005 and 2006, there was a series of papers by Ivan Damgard and Serge Fair and Louis Salvay, Christian Schaffner, and then Renner came along and they published another paper where they kind of improved the analysis. So in these two papers, they introduced this thing called the bounded quantum storage model. Okay, and it turns out that if you have this assumption, then information theoretically says secure OT suddenly becomes possible. And we
But
are
this
going
is
to
still
talk
device
about.
dependent, right?
This is still
they're
device
trusting the
dependent.
quantum device. Okay. Yeah.
Yes, absolutely. This is still device dependent. So I'm going to like the goal of the talk is basically explain each of these terms one by one. Yeah.
Right. Sorry for the interruption. Just
No,
got
no, no,
excited.
no, no,
Carry
no
on.
problem. Yeah. So the next few slides will basically be the answer to the question, what is this bounded quantum storage business? Okay, like what magic does it hold that it suddenly makes OT, information theoretically secure, OT possible? So this assumption is actually you can kind of explain it in both in two ways. One is a very practically motivated way. For example, if you guys have any idea about like the kind of hardware that people are using in labs, or the kind of experiments that have been done, you would know that like good quantum memory, which can hold quantum states with high fidelity for a very long time, they don't exist yet. Okay, so even if you store your quantum state, let's say like diamond or like some diamond side kind of memory, if you store a quantum state in that, the highest record I think that has been achieved is at most half an hour or something. Not even that. After that time, the quantum correlations in your quantum memory storage device kind of disappear. Or as the physicists would put it, decoherence happens. Okay, so we model decoherence as basically the following operation: that nature comes in and nature kind of measures all of the registers of your quantum state along the computational basis. So for example, if you were, let's say, storing one EPR pair, like one half of an EPR pair in your memory, and somebody else was storing on the other half of the EPR pair. After, let's say, 5 minutes, some massive amount of degradation will happen, and nature will kind of come in and measure the half of the EPR pair that you have in computational basis. And after that, when you kind of try to probe that state, you will see that it's not quantum anymore. It does not have any quantumness, whatever that means, anymore. It's basically become something classical. Okay, so this practical uh, issue kind of leads to the BQSM assumption, where we assume that like it's slightly more simple than what I just said. What I just said is actually fully captured by something called the noisy quantum storage, NQSM, but that's mathematically very difficult to deal with. But this is like a slightly simpler model, where you assume that up till a certain amount of time your memory is perfect. Within that time, the adversary is allowed to do arbitrarily complicated or absolutely computationally unbounded operations on the quantum state that they hold. But once that amount of time is done, the BQSM assumption is imposed, and all of the quantum states essentially become classical. Now, you might have noticed that there is a star here, and I will explain why that star is there in the next slide. But for now, just assume that this is what it means, that after the, like, at some point the BQSM assumption is imposed, and once it is imposed, everything essentially becomes classical. Okay, in our paper we kind of use the notation delay to denote the imposition of this assumption, that before delay the adversary is allowed to do arbitrary things. We have no bounds on that, but after delay, whatever state the adversary holds has become a classical state. Now, so I said that there is, like, this is one way to explain BQSM, but there is actually another way, which is a more complexity theoretic way. So when we impose computational bounds, what actually are we imposing? We are imposing time bounds, right? You can think of BQSM as a space bound. So instead of putting a bound on time, the BQSM assumption essentially puts a space bound on the quantum memory of your adversary, not on the classical memory, on the quantum memory. And this actually, I'm mentioning this for a very good reason, because even in classical cryptography, Maurer introduced bounded memory assumptions and showed some very nice results early on. And in fact, the bounded quantum memory was inspired from Maurer's work in the classical domain. But that's just an aside.
So in the bounded classical memory, can we also construct these OT protocols? Do you know?
I think no, not quite. I don't think so. I think you can get commitment schemes, but you can't get OT. But I'll have to check. I think you can get commitment schemes. I think Mauro showed that you can get commitment schemes, as in bit commitment and so on.
Oh, okay. That's wild. Okay, thank you. Didn't know that.
No,
Okay.
but I might be wrong. I might be wrong. Don't quote me on this.
No,
Like,
I'll look it up. Yeah, don't worry.
Yeah.
Carry on. Sorry.
But this is actually like, I think okay, I'll send you guys the references after the talk, maybe tomorrow or something. But actually that sequence of work didn't become very popular because there is no shortage of classical memory. But the same cannot be said for quantum, because there is a huge question now whether we can actually make quantum memory, although it increasingly seems like that we can. But yeah, it's still an interesting result. But anyway, so the thing is that this assumption that like there's a star here, right? So whatever I said here, it's not really bounded. It's more like zero quantum memory, because after the assumption is imposed, I'm not allowing the adversary to really keep anything quote unquote quantum. But the BQSM allows actually allows the adversary to retain some quantumness. Okay, so for example, if you have an n qubit state, it is allowable that after the BQSM assumption is imposed, the adversary can maintain, let's say, some small fraction gamma n of the qubits as they were before. Okay, so this is typically the model in which BQSM protocols are defined, that a small amount of memory is retained. Like you allow the adversary to kind of do that. But and how much you allow the adversary to retain will kind of depend on your protocol and how much min entropy you can get out of it. So that is protocol dependent, but this kind of makes it a much more general model. Okay, but for the purpose of this talk, we are basically going to assume not BQSM but ZQSM. But whatever I'm going to say, all our results actually extend to the general BQSM model, where even if I allow the adversary to retain some small gamma n amount of quantum memory, it still works. Okay, so
your results are going to be as a function of gamma. Sorry for the interruption. So your results would depend on gamma rate in the end. Okay.
Yeah, okay. Yes, absolutely.
And what happens, like for instance, if instead of gamma you had, I don't know, like log n memory or something like this,
then you're complete. So the thing is, like, sorry, someone say something.
Shreds, were you guys saying something? We heard something.
Yeah.
Okay, maybe not. Sorry.
No.
Yeah. So the thing is, like, where does that gamma really pop up, right? So that gamma is a fraction between 0 and 1. Yeah. And the place it pops up is essentially you have these min entropy bounds, like h min of x conditioned on, let's say, some e y. Okay. And that E will be your quantum memory. Now what you, like, the way usually these things go is you have a lower bound on h min x given y. Let's say that's like n/2, right? But when you introduce that E, you have to use these min entropy chain rules and say like h min x condition on xe is greater than equal to n/2 minus the log the size of E. Okay, so this log the size of E will essentially be your gamma n. Okay, so then that gamma has to be less than half. So it doesn't really make sense to say that it's log n.
Right. Like it doesn't at least fit in the formalism very clearly. Okay, got it. I was just thinking in terms of complexity theory. Like we normally don't care about, like, if I didn't know about all of this min entropy business, I would have imagined that constants don't matter so much, and I would care more about the scaling with n rather than the coefficient. But okay, I see what you're saying. Okay,
yeah, thanks. In this setup, the constants kind of do matter. Unfortunately, in our paper, like the paper got so complicated that we just like stated without proof that this works, and we could do that because if you prove it for ZQSM, generalizing it for BQSM is a very standard trick. So there is no explicitly written bound in the paper that this is how it will work. But if you have like some experience in working with the BQSM, you can kind of work it out. But I would have kind of preferred that we write it, but the paper anyways it became like 75 pages, so we kind of said, what, screw it. So for the rest of the talk, the mantra will be after delay, everything is classical. Okay.
So just before, just one small clarification. You mentioned that going from ZQSM back to BQSM.
Sorry, my accent has become like ZZ.
No. Sorry, that's not what I was asking. Sorry, no. I understand. Yeah, I mean that's the American/Canadian thing. Well, no, Canadians also say. Anyway, that's not the point. The point is that the ZQSM, going from ZQSM to BQSM, you said is a standard trick. So is there like a general theorem that says that certain results can be mapped directly, or is it?
It's basically folklore because like people have used that trick in multiple papers over and over again, and
I see.
yeah.
Okay.
I mean, I can point you guys to some references if you want. Like there are, but the best references are essentially these two works, and in fact this one is extremely well written.
Got it. Thank you so much.
Yeah.
Thank you.
Yeah.
Okay.
So
sorry, I had a small question as well. So how can we quantify this delay? So like, is it like?
Do you mean mathematically or practically? Because the answer will depend on what you want. Oh, mathematically, we literally say that if you're being super precise, you say that whatever protocol you design, that protocol is based on a certain clock. So there exists a clock. Like we are computer scientists, so we'll think of time as maybe discrete. So you have a clock, and let's say after a certain number of ticks of the clock, like till those number of ticks, you allow the adversary to do everything. Let's say maybe 10 ticks. Okay. But after 10 ticks, everything will become classical. Like there will be a global operation by some entity called nature, and that global operation will be a computational basis measurement on all registers that exist in the system.
Right.
Yeah. So this is kind of how you.
Sorry. So it's not just the adversary that becomes like whose memory gets packed.
It's everybody. It's everybody. Every party in the protocol.
Okay. Right.
Hello.
But that's yes.
Yeah, in one tick, like do you apply one gate from some universal gate set, or like what can you do in?
Oh, yeah. So what you're talking about is basically you're trying to map what I'm saying to the circuit model. You don't need to assume any kind of so like what you're saying kind of means that you want to build a circuit for what the adversary is doing. But here you don't need to do that, because whatever we are going to say will allow the adversary to use arbitrary unitary operators. Even unitaries which cannot be captured by universal gate sets exactly, or like approximations would be very, very bad. Even those kind of unitaries we will allow the adversary to have. So any unitary in SUN is allowed.
Right.
Okay. And at every time, as you said, at every tick of the clock, this adversary might have like a hugely complicated unitary, and then you compose all of those unitaries together, and that is essentially the adversary's action.
Right.
So what is the difference between, say, the 9th tick and the 10th tick?
Oh, the difference would, first of all, like that's very generic, because the difference, like it depends on whether you're looking at the adversary or whether you're looking at the honest parties, right? So for the honest parties, it does make a difference. For the honest parties, because at every tick of the protocol, the honest parties need to do something, 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 something. But no such, there is no such imposition on the adversary itself. The adversary might decide to do nothing. He might decide to like impose, like do the entire complicated unitary at the very end, or like distribute it. We don't really know. We have no assumption on what the adversary is doing. All we know is what quantum theory allows us to know, which is that at the end of the day, we can model the entire composed action of the adversary as one big unitary operator, or even an isometry, like if you allow ancilla qubits.
So in some sense, these sticks capture like rounds, where in some rounds you can do nothing, or
Not quite. When you say, see, when you say a round, you assume that there is back and forth communication. So that word is a little loaded, but I kind of understand what you're saying. You're saying that like at each tick there is some action that is happening. Like maybe some party is doing something. Like you specify that at this tick, Alice does this measurement. At the next tick, Alice sends these bits. Yes, absolutely. That is absolutely correct. But let's not use the word rounds, because round has a very specific meaning in crypto. But what you said, other than that verbiage, what you said is absolutely correct.
right.
Okay. Questions? More questions? Okay. So I'll go ahead. Now, as I kind of pointed out, the main power of this BQSM lies in forcing the adversary to measure the registers, because otherwise what happens is the adversary can essentially store whatever quantum states they have forever, right? And the adversary, remember, is watching the communication between Alice and Bob. And Alice and Bob, we don't assume that Alice and Bob have any sort of secure communication channel. Any communication that they do uh, has to, sorry, there is no adversary. What the hell am I saying? So sorry. Yeah. So like Alice and Bob are communicating, but remember, at some point Alice might have to reveal some information that she has to Bob. Okay. And potentially that information might reveal things that Alice doesn't want to reveal. Okay. But what the BQSM assumption does is it forces the the adversary to do the measurement. And the intuition is that once you do the measurement, all quantum correlations are essentially destroyed. Okay. And then the adversary can't really do anything more. We'll see what precisely what this means in the coming slides. But this is essentially the idea that, that any kind of quantum cheating that the adversary could have done is no longer doable once the BQSM assumption is imposed. And using this precisely this observation, Damgard and collaborators showed that information theoretically secure OT protocols are possible in the BQSM model. And in fact, recently, Louis and his student Mohammad Barhush, they did some fantastic work where they showed that even more surprising and even more impossible in some sense uh, primitives are possible in the BQSM model. Check out this paper if you guys are interested, but they came up with some really fantastic results in this model. Okay, so I'm just gonna go ahead.
Wait, sorry. I thought
Yeah.
wasn't OT already universal? So how are they coming up with more
Uh,
things?
no, the stuff that they came up with, um, that is kind of I think it's beyond secure multi-party computation. So, for example,
What?
one
What is beyond secure multi-party computation? Cool, tell me.
yeah, so there's this primitive called what's it called? One-time programs, right? So
Ah,
a
sure.
one-time
Okay.
yeah.
Okay.
So they showed that yeah, you immediately understood. So they showed one-time programs become possible in BQSM, and then they strengthened one-time programs to something like entirely new called program broadcast, where you're basically broadcasting your program, but the unintended party can't really get anything out of it. It's a fantastic piece of work. You should
Nice.
absolutely take a look at it. Yes.
I see. We had a talk on one-time programs, so that's why we were. But I didn't know. I wasn't. Yeah, I somehow missed this specific work. So thank you for pointing it
So
out. I'll try to know.
the thing is like Louis and all, Louis et al are like very. They don't really advertise these things too much. I only know about it because there's a very nice series of talks that happens in like Quebec and Ontario every year called Quorum. And basically,
Nice.
like all of the quantum people here show up, like Anne Broadbent and
Nice.
our group and
Right.
Cloud Crypto, all of us showed up, and that's where I saw this talk, and then I spoke to Louis about it.
Sounds good. Thank you.
Yeah,
Thank you. We'll probably invite them as well. Thank you. Okay.
absolutely. I'll let them know. Okay, so now we are going to go to the heart of Atul's comment that like all of this stuff that we saw so far, or that I've mentioned so far, all of this stuff kind of has this implicit assumption that that whatever specification I write down for the protocol, that for example Damgard and collaborators, this protocol kind of assumes that the honest party can produce BB84 states, that is computational basis states 0 and 1, and Hadamard basis states plus and minus. Yeah, these are called BB84 states, and it also assumes that Bob and Alice both can do measurements along these bases. But suppose you think slightly more practically, that actually, you know what, the people who are enacting these protocols, they are going to be organizations like banks or governments and so on, right? Like these are organizations, you don't often expect them to have ready-made quantum labs or something unless they're the US government. Often what will more often what will happen is that they're going to buy this hardware from some vendor, and it is entirely possible that the guy with whom you want to do this protocol, that guy has kind of bribed the vendor. For example, like if India was buying some stuff from the Chinese, right? It's not just possible. It's maybe a very prudent assumption to make that there is some Chinese bullshittery going on inside, right? So you can't really trust your hardware. But if you but this hardware is not classical hardware. Classical hardware is still testable. It might take a long time, but it's still testable. You can open up the hood and see what the hell is going on inside. Quantum hardware is not even testable in that sense, because quantum hardware means that you have one port and somebody else has the other port, and these two ports are kind of sharing uh, entanglement or some state. Like the moment you open up that box that you have, the state will essentially dissipate because of noise and so on, whatever open up means. So it's not really clear how to certify quantum boxes, quote unquote, code boxes. Okay, and this is where the idea of device independent protocols uh, come in, right? Um, oh, I actually said all of this. Sorry. Yeah. So this is basically the idea.
Self-testing here? Sorry.
Sorry.
Self-testing kind of thing here?
Yes. Yes.
Okay.
Absolutely. So we are heading towards self-testing. Yes. So the way it turns out that there is like this magical way where you can actually certify quantum devices. And when I say device, I mean very precisely, I mean the following thing: the state being shared between the ports and the measurements themselves that the ports are enacting on the registers of that state. Okay, so the way to do it is by playing some sort of a non-local game and checking whether you're winning the whether you're winning the non-local game with a certain probability or not. Now it turns out that if this condition is satisfied by something called a rigidity theorem, which you'll see, you can actually guarantee that the state being shared is very close to the ideal state that you wanted, and the measurements are also in some sense close to the ideal measurements that you wanted. And in our protocol, the protocol we're going to see pretty soon, we are going to use this game called the quantum magic square game. So the next few slides, I'm going to talk about magic square. Questions before I move on? Okay. So the classical Magic Square game is specified as follows. You have a referee and you have two parties, Alice and Bob. And the referee, oh, right. So one assumption is that, like, notice that there is this dotted line. This dotted line means that Alice and Bob are not allowed to communicate. Okay. Um, Now, the game is as follows. So the referee sends Alice and Bob questions. So the referee sends Alice her question X and Bob his question Y. And each of these questions are sampled uniformly at random from the set 01 and from set 012. Okay. Then, given her question, Alice is going to answer with a 3-bit string. So suppose X was 0, then Alice would answer with some string, 3-bit string, A0, A1, A2. And notice that I have drawn this as a row. Okay. And similarly for Bob, Bob will answer with a 3-bit string depending on his question, B0, B1, B2. This is the structure of the game. And they kind of send their answers to the referee. So the black arrows are like go out first. These are the questions, and the red arrows are the answers. Now, what is the winning condition for this game? Is you essentially need 3 conditions. Number 1, the parity of Alice's answers should be even. The parity of Bob's answers should be odd. And the last thing, this is that the common bit should be the same. Now, what do I mean by the common bit? So, for example, let's say Alice's question was 0, x equal to 0, okay? And let's say Bob's question was y equal to 1. And Alice answered with A0, A1, A2. You guys can see my cursor, right? My mouse cursor?
Yes, we can see it.
Okay, great. And Bob answered with B0, B1, B2. Now you see why I drew these as rows and columns of a matrix. Yes.
Yeah, so like the room, suddenly the network got off and like we did not catch up to the part, like, okay, the string A's are a row. After that, like everything was lost.
Oh, sorry. So no. All I said was that like Alice answers with a row and like of 3 bits, A0, A1, A2, and Bob also answers with 3 bits, but we're going to draw it as a column. That's it. And then the next thing is that I was talking about the winning condition. Like these 3 conditions, if they are all satisfied at the same time, then the referee declares that Alice and Bob have won. If even one of these conditions is not satisfied, then the referee will say that they have lost. Okay. So the first condition is that the parity of Alice's answer, like A0 XOR A1 XOR A2, that has to be 0, as in there have to be an even number of ones. Okay, so the parity has to be even. Similarly, the parity of Bob's answers should be odd. Okay, and the last condition is that the common bit, and I'll define what I mean by common bit. The common bit has to be the same in both. So to see what this common bit business is, let's assume that Alice's question was x equal to 0 and Bob's question was y equal to 1. Okay. So corresponding to x equal to 0, we have this row A0, A1, A2, and corresponding to y equal to 1, I just place B0, B1, B2 at this column. So y is basically the column number. I mean, it's a matrix, right? And x is the row number. The common bit would essentially be the place where Bob's answer written as this matrix and Alice's answer written as this matrix coincide. In this example, it's this red square. So the 2 bits on this red square for Alice and Bob have to be the same. That is this condition. A sub y and B sub x have to be equal. Is this clear to everybody?
Yes. Thank you.
Okay, cool. Okay, so now, how well do classical strategies do? Firstly, what is a classical strategy, right? So a classical strategy would basically be a table like this, which Alice and Bob both know a priori. So let's try to fill up this table according to Alice's condition. according to Alice's parity condition. So each row has even parity. That means that the whole table has even parity. But that also means that there is at least one column which does not satisfy Bob's odd parity condition, because like if there are an even number of ones in all, there is at least one column where you don't have an odd number of ones. There have to be an even number of ones, right? So filling up a table like this where both conditions 1 and condition 2 are satisfied at the same time is kind of impossible. Okay. So what does Bob do? So Bob can have a deterministic deterministic strategy like this, that whenever, like this is the way he can cheat, that whenever his input is, let's say 2, y equal to 2, like he's asked to output column 2, he will just flip the first bit. He'll just flip C02. Okay. But this has a problem. The problem is that there is a case when C02 is the common bit. That case is when x equal to 0 and y equal to 2. In that case, Alice will output C02 as it is in the table. And Alice, remember, does not know what Bob's input is. But Bob will be outputting the flipped version of C02, that is C02 complement. So in that case, their answers will not match. That is, condition 3 will not be satisfied. So there is always a case when they are going to lose, even if Bob has this very simple cheating strategy. Okay. And what is the probability with which this condition happens? It's exactly 1/9, because 1/3 x equal to 0 with 1/3 and y equal to 2 with 1/3. So with probability 1/9, they lose the game. And it turns out, actually from this, it's very easy to prove that the best possible probability with which Alice and Bob can win the Magic Square game is actually 8/9. Okay. Was this clear to everybody?
Yeah.
Okay, great. Now here
So,
comes.
so I guess the final proof is just saying that I guess that it would just be a convex combination of deterministic strategies, and for every deterministic strategy there would be at least one inconsistent assignment. And right,
exactly.
That's
it.
Okay.
That's exactly it. That even randomized strategies are basically like it's like a decision tree kind of thing, right? That it's a distribution over deterministic strategies, and each deterministic strategy looks like this. So you can't do better than that. Hello?
Right. Yeah.
Yeah. Okay.
So
yeah, question. Yeah, that's a question.
We say that Bob wins. Like, when do we say that Bob wins?
No, Alice and Bob both have to win together. It's not that either Bob wins or Alice wins.
Then
so it's like CHSH, but
then they can just like have some pre-shared strategy, right? Which will like help them win for.
This is their pre-shared strategy. This is exactly the pre-shared strategy. Like Alice has a copy of this board and Bob has a copy of this board.
Why would Bob try to cheat?
No, because if he doesn't do that, so if he doesn't flip the bit, then he's going to output a column which does not satisfy condition 2. Then he loses anyway. So you might say that, okay, maybe he cheats. Maybe he cheats so that he gets condition 2 to be satisfied. Okay. But if he does that, then condition 3 is not going to be satisfied. So there is at least going to be one constraint among these three which is going to fail. That's the idea.
Right.
Okay.
Okay.
Okay. So the really cool thing is, like this is one of those demonstrations where something magical happens. It turns out that there is a quantum strategy. And when I say quantum strategy, I mean that Alice and Bob share some entangled state and they do some sort of measurements. There is a quantum strategy which wins this game with probability 1. And this is kind of insane. Because as we just saw, no classical strategy, no randomized classical strategy can ever win this game with probability greater than 8/9. But there is a quantum strategy which can. Now I'm just going to go out of full screen mode for a second because I want to show you guys something. Because the next slide is going to be pretty scary. But I want to show you the less scary version first. Magic. So I should have opened this beforehand. Sorry. What? Quantum magic square. Yeah. So. Yeah. Hey. Shit. Yeah. Okay. So, what is the strategy? So, when we say a quantum strategy, we have to specify two things. We have to specify the state that is shared between Alice and Bob, and we have to specify the measurements that they do. Okay. So the state that will be shared between Alice and Bob for this probability one strategy is going to be two EPR pairs, like EPR tensor EPR. Now, what are the measurements going to be? Those measurements are given by the eigenvectors of these observables. Okay. So what this table is telling you is that if Alice gets x equal to 0, she is going to measure these observables in row 0. Notice that these observables commute, so the distribution is going to be fine. Like there is, it doesn't depend on the order of the measurement. Okay, and this is actually true for each row and each column. And when Bob gets a column number, he's going to measure the observables along that column. Okay, and in fact along the column the observables also commute. Since Alice and Bob's observables are common at one cell, for that particular measurement their bits are going to coincide. I'll explain what this means in a bit, but does everybody know what measuring an observable means? Does everybody know this?
Yeah,
Yes.
I mean,
Yes.
they are all familiar
cool.
with quantum.
Oh, nice, brilliant. Okay, but unfortunately for our case we are not going to be talking about observables. We are actually going to specify the operator picture, we are actually going to specify the PVMs. So this is the scary picture. Okay, it's an extremely scary picture, but no need to be afraid, because essentially that table that I showed you guys on Wikipedia, if you break down those observables along their eigenvectors, right, essentially you get these PVMs, and these PVMs correspond, constitute the measurement that you're going to be doing. For example, remember that the first entry was I tensor. Actually, this table is a little skewed, but right, this should be like Z tensor I, but it's the same thing. Okay, so if the first entry was Z tensor I, then the two PVMs that you get corresponding to outcome 0 and outcome 1 would be Kedbra 0 tensor identity and Kedbra 1 tensor identity. So you do that same thing for every cell and you get this table. This is due to Rahul's student Sujita Kundu and Jamie Sikora and Ernest Sam. They are not the first guys to come up with this table, but they have this very beautiful paper where they actually explain this thing very nicely. Okay, like they were the first people to actually write down this table explicitly, so I'm going to credit them here. And this is an extremely beautiful paper. Give it a read if you have some time. But anyway,
Yeah,
so
what is the title of the paper? Do you remember?
Yeah, device independent protocols for XOR rotation.
I see. Okay. And what was so nice about the table that they, I mean, like, did they comment on why this is important, or?
Yeah, so essentially, see, that paper, it's not really a crypto paper. Okay, I mean, they don't have a cryptographic protocol per se. in the sense that we understand cryptographic protocols. Like you don't have a security parameter, and you don't like show that things are niggle, blah blah blah. What they show instead, what they investigate instead is, okay, suppose I give you one iteration of the magic square game. Can you use that to come up with a completely device independent protocol for OT without any assumptions? Now, obviously, this is impossible. So what they say that, you know what, I'm going to completely ignore these cryptographic definitions, and what I'm going to investigate instead is what are the maximum cheating probabilities that I can have for Alice and Bob in this setting, which is like the worst possible setting. And they use the magic square game to that effect. So
I see. Okay.
So that's kind of where this stuff all got started, and we have used these operators, like the structure of these operators, very explicitly in our work as well.
I see. Okay, thanks.
Yeah. So so the point is that yeah. So what is Alice's strategy? Suppose Alice gets 0. Okay, so she's going to measure both her qubits. Remember, she has 2 qubits, like one half of one EPR pair and one half of another EPR pair. So she's going to measure one half of her qubits with first this guy, then this guy, and then this guy. And all of these commute. You can easily show that. So order doesn't really matter. What does Bob do? Suppose Bob gets 0 as well. So Bob measures his qubits with this guy, and then this guy. Now, suppose that Alice's first measurement gave an outcome 0, and her second measurement gave an outcome 1. So her end of the state collapsed to Kedbra 0, Kedbra 0, tensor Kedbra 1. But since they are sharing 2 EPR pairs, that means that Bob's end of the thing also collapsed to Kedbra 0, tensor Kedbra 1. Now when Bob is measuring, he measures his first qubit with again along the computation basis. But that, remember, has already collapsed to Kedbra 0. So he's going to get the outcome 0 with probability 1. And this phenomena happens for every single common cell. So you can basically ensure that they win the game with probability 1. Is this clear to everyone? Okay. Okay, cool. Now, there are some curious properties. By the way, Atul, how much time do I have left?
Yeah, I was going to mention we have like about half an hour because we started at 3:30. So sorry, I think we had too many questions. So yeah, maybe we can tone down the questions and you can, continue.
No, it's fine, it's fine. So the thing is that I don't have, oh man, I have a lot of slides left. But okay, fine, we'll see. So there are some curious properties that I want to kind of point out first. One is this common bit thing that we saw. But another extremely, but like, what is the distribution of the common bit? It's going to be a uniformly random common bit. Okay. But another curious property, which we don't find in CHSH at all, is that even if you condition on, let's say, Bob's outcomes, Bob's 3 bits, and you pick any one of the 2 other bits that Alice has, the distribution of that bit is going to be completely uniform. So to see this, let's go back to the table. Suppose that again Alice got 0 and Bob got 0. Okay, so Alice measured like this, and she got, let's say, 0, 1, and it has to be even, right? So 1. Okay, so 0, 1, 1. So her state is Kedbra 0, tensor Kedbra 1. This is the same thing that happened on Bob's end. On his end, he has Kedbra 0, tensor Kedbra 1. But now, when he measures, he gets Kedbra 0 on the first qubit. But on the second qubit, where he has a Kedbra 1, he's actually measuring along the Hadamard basis. So he's going to get a completely random bit. So this is what I meant. That even if you condition on one player's entire outcome, the only thing common is really the common bit. Every other bit is going to be completely random. Okay. So you condition on this guy, or you condition on this guy. A0, which is not the common bit, even in that condition space, is going to be completely uniform. And this is super, super important for us.
So here we are sort of assuming some kind of rigidity already, right? For the
Yes.
magic square.
Yeah, I'm coming to that. Yeah, that's the next slide. Yeah. So from this, from these properties, we get our first toy protocol for OT. And what is the toy protocol? So assume that like this is device dependent. This toy protocol is going to be device dependent, as in we assume that the like something perfect is happening perfectly. So let's say Alice and Bob are sharing two EPRs and play the magic square game as per the perfect quantum strategy. And you make these extremely restrictive assumptions that the adversary, whoever the adversary is, either Alice or Bob, they cannot really open their port and do arbitrary things. Also, extremely important, no communication is allowed between the ports. And this is important because we are playing the magic square game. If you allow communication, then the whole structure of magic square kind of collapses. It doesn't make sense anymore. Okay. And one more assumption, which I'm not going to go into, that only classical input and classical outputs are allowed. But this assumption is kind of subsumed by the assumption that the ports cannot be opened. Okay. But I'm only making these assumptions because this is our first toy protocol. Okay. Now, given these assumptions, let's design a protocol for OT. So let's say you have these boxes, one where if you have the same letter, sorry, if you have the same number, you belong to the same. You're essentially playing the same copy of the magic square game. So 1A and 1B share two EPR pairs, and they're implementing the magic square measurements on the 1A and 1B registers. And 1A, 1B together is one big magic square device. So that is in tensor with 2A, 2B. That those two are in tensor with 3A, 3B, blah, blah, blah. So everything is independent and everything is absolutely perfect. The world is very nice here. Okay. So what happens now is that Alice samples randomly and uniformly at random her inputs x1 to xn, and he just inputs them into these boxes. So these like xi serves as the input to the box IA. But Bob, who remember has to have only a choice bit C, which is between 0 and 1, he is going to input the same choice bit in each one of his ports. Okay. Now, once they have sent in these inputs, Alice gets her outputs, blah, 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 the rows, and Bob gets his outputs. Okay, the columns. This is, I guess, clear to everyone, right? Okay. So first, hello? Was there a question? I thought I heard something.
No. I think all is clear.
Okay, good. So Alice has these outputs. Let us call them like A1, A2, and AN, and Bob has these outputs B1, B2, Bn. What Alice does after the delay? So the delay has happened and the states have decohered and like there is no quantumness left. After the delay, Alice needs to tell Bob where the common bit is. How does she do this? She's literally going to send Bob her inputs. But this has to happen, remember, after the delay, because if it happens before the delay, then Bob can start cheating. He can actually do the exact same measurement that Alice did and recover everything. So that doesn't work. So you have to wait for the delay for the quantum states to get destroyed. And then Alice is going to send all of her inputs to Bob. So once Bob gets Alice's inputs, x1, x2, xn, he knows exactly where to look. So he will look at, let's say, x1 for b1, and if x1 is 1, he knows that the common bit is situated in the middle in this red square. For b2, if x2 is 0, he knows that the first one, like the 0th one, is the common bit. What does Alice do? So on Alice's side, this line that I have drawn, these are the common bits. Okay. So Bob and Alice now have two strings on which they agree. Bob knows what this string is. Alice knows what this string is. Okay. But remember this property that even conditioned on B1, B2, Bn, if you look at the distribution of another bit in Alice's answers, that distribution is going to be completely uniform, and that is the second line that I've drawn. Don't know if you guys can see the color. Like, I'm not very good at this, but there's like a green coloring here. So on Alice's second column, the distribution of the bits in Alice's second column, this column, condition on Bob's answers. This column is completely uniformly at random. And now I think the protocol is becoming slightly clear. So Alice declares that her bit S0 is going to be the XOR of the first column of the common bits. S1 is going to be the XOR of the bits in the second column, or the green bits. Okay. Alice doesn't know which is red, which is green. She just does this blindly. She will take the XOR of all of the bits in the first column, and she will take the XOR of all of the bits in the second column. But after she has sent Bob her inputs, Bob can only know one of these columns, and the other column is going to be completely random to him. Okay. So he gets to know only one of these guys. The other one, because of the randomness, is completely independent of whatever he has. Okay. Is this clear, everybody?
So far it's essentially what Jamie and others had, right? Like Sikora and
Pretty much.
Kundu and others.
Pretty
Right? So far it's the same review. Okay.
Yes, exactly. No, actually, they don't even have like A1 to AN. They don't have this. They do it for
I
like
see.
one device.
For
They do
single
it for one
shot.
device. Single shot.
Right.
Yeah. That's why it's not a cryptographic protocol.
I see,
Because
I
like
see.
and they have no assumptions. They have no BQ, no computational or
Yeah.
memory bound.
Exactly. They don't have a way to enforce that you're somehow removing one of the. Okay.
Exactly.
Got it. Thanks.
Exactly. So great. I'm going to kind of like skip these observations because it's not really important for what we're doing. Now, all of you might have noticed a major problem with what I just said. Like, this all is very pretty, fine, but it kind of assumes that Alice and Bob's devices are playing Magic Square perfectly. What use is that? Because they might not be playing Magic Square, right? I mean, there are some other things that I wanted to say, but because of the paucity of time, I'm just going to skip over them. The thing is that the reason we went to Magic Square in the first place was because Magic Square is self-testable. Magic Square admits something called a rigidity property. So what you can do is you can set aside, like, okay, still let's like keep this assumption that each of the devices are in tensor to each other. Okay, let us maintain that assumption for now. But given that assumption, you can kind of select a random subset of the devices and check whether like how many of those devices is winning the Magic Square game. That will kind of give you an estimate as to how many of the devices are actually good. Okay, and because you selected a random subset, that subset is going to be pretty representative of the other guys. Okay, so once you do that, there is a theorem for these sort of games. These are like in general called XOR games, but for these sort of games, there's a theorem that if you tell me that you are winning the Magic Square game with probability at least 1 minus epsilon, then I will tell you that the strategy, whatever strategy you're using, it's going to be very close to the perfect quantum strategy. And this, at least to me, this is absolutely insane. This is saying that if you tell me that you're winning this game with very high probability, then I will tell you that you're not doing some arbitrary bullshit. That actually whatever measurements and whatever measurements you're doing and whatever state you're sharing, even if it's defined on like larger spaces, not 2 qubit or 3 qubit spaces, even if it is defined on larger spaces, up to local isometries, you are actually playing the perfect Magic Square strategy, and everything else you're sharing on the larger spaces is just junk. Okay, so this is kind of a leash. This is a leash on quantum strategy, and this is very quantum specific. I don't know of anything in the classical world which has this property. And this property is called the rigidity theorem. Okay, and Magic Square satisfies the rigidity. CHSH satisfies the rigidity. I'll just flash the statement from Srijita's paper. It's again extremely scary, and I'm not going to dwell too much on this, but believe me when I say, like, what are the important parts of it? Like, suppose the device wins with probability blah blah, then blah blah happens. And see, these states and these measurements are like the perfect measurement operators and the perfect state. Okay, so in some sense, you can, if you can guarantee that your device wins the magic square game with some lower bounded probability, then you can kind of immediately say that, yeah, that device is playing the magic square game almost perfectly. Is this clear to everyone? Like, more or less?
Yeah.
Okay. So I call this smoothed rigidity because, like, the rigidity is historically it has been referred to for like strategies which win with exactly probability one. This is smoothed because there's a threshold term here and we need that. But yeah, this is essentially what I was saying earlier. So all we really need to do is find the winning probability of the device. And if you have this assumption, so now we are moving to toy protocol 2 and we are pretty much at the end of our talk. In toy protocol 2, if you make this super simplifying and very constrictive assumption that each device is completely identical and each device wins the game with some probability p win, then what can you do? You can basically uh, like select a random subset of the boxes, just play the magic square game as is on. Like Alice can send Bob his inputs and say that, okay, you know what, you just send me, like, okay, so like suppose this is a test box. Okay, so on the test box Alice can send Bob an input that he has to provide, and then Bob simply has to answer back. So she can do this for a random subset of the boxes, and she can basically count. And since we assume that each device is identical, using the Chernoff bound, we are going to get a very good estimate of what this p win is. And if we know that this p win, like if this p win is greater than some threshold value, like 1 minus epsilon threshold, then you know that magic square applies. And because of the assumption again that each device is identical and in tensor with each other, this assumption will guarantee that each of these boxes, whatever boxes that you didn't test on, they are basically perfect. Okay.
So I have a small question. So here, are we admitting, like, are we including adversaries that, say, for example, Bob is malicious and Bob prepared the devices, right? And then maybe potentially Bob lies to pass the test. Do we consider
Yes.
such things here, or?
Let's not. Let's push it to the final slide. Like Bob can lie.
Okay, carry on. Yeah.
But Bob can basically lie, but it's not going to do him any good here because, like, if he lies, he can't really win the game by lying unless you're sharing EPR, unless you're actually enacting the perfect strategy.
Not necessarily, right? That is only the case if Bob somehow
if you
did
have
not
this
prepare
assumption.
the device. Yeah, exactly.
If you have this assumption, like this assumption,
Okay,
that's
carry
why
on. You only have 10 minutes, so yeah. Sorry. I shouldn't interrupt.
Okay, so again, I mean that was actually a very good question because it highlights this point that this estimation and this strategy only works because we made the assumption that each of the devices are independent and they're completely identical. This is called the IID assumption. Okay, and another assumption which was also pointed out by Atul is indirectly is that Bob is really not allowed to open the boxes. He might have prepared the boxes, but after preparation, he's not allowed to open the boxes and do arbitrary things. Okay. So, okay. So we saw two toy protocols. And now let's see the assumptions that we made to get to this point. We made the assumption that each device is identical and wins with the same probability. We made the assumption that the devices are independent of each other. And the adversary can't really open their ports to do arbitrary things. And the no communication assumption always has to be there. It's not something you can really remove. And also only classical inputs and outputs. But again, this was kind of subsumed by the adversary can't open their ports or something. Okay. So the final boss, if any of you play games, you will understand what this word means, is basically removing all of these assumptions at the same time. This is extremely difficult. As you can tell, it's extremely difficult because like there are a number of places where you will fail. How do you even do testing? Because on some places it might be good, but like conditioned on if there is arbitrary entanglement across the devices, if the measurements are joint measurements, what does it even mean to give a guarantee after your test passes? These questions
Sorry,
come up. So
in the when you're doing the test, are you somehow you must crucially rely on the fact that you're in the bounded storage model, right? Because
absolutely,
otherwise you could just do
absolutely,
coin flipping, right? If you could like
absolutely,
somehow
absolutely,
test it. Okay,
absolutely.
okay.
Bounded storage is very, 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 very important here.
I see.
So the point is that we are now
So
like this is
sorry, can
yeah.
I just ask one quick follow-up? So you're essentially
Sure,
saying
sure.
you can do self-testing in this adversarial sort of setup in the bounded storage model as a maybe a
Yes.
corollary of what one of the things you're doing.
Yes. No. Not quite. That is a project that we have going on with Fred here. I will be very happy to talk to you about it later. And what the results we have are much stronger there. Okay, like we have not only do we have self testing, we have entanglement certification, but you can basically recover. You don't need to test all of the entanglement. You can recover the entanglement later. Like this is going to appear in the on the archive, hopefully in the next couple of months if everything works out. But I can speak to you about that later. But very good
Okay,
observation.
let's discuss later. Yeah, okay.
Yeah. So so the final boss is basically this, that none of these assumptions apply. The states being shared across your devices might be arbitrarily entangled. The measurements being made on Alice and Bob sports might be arbitrary joint measurements. So the question is, how the hell do you design device independent protocols in a setting that is this complicated, where you have essentially no structure? And I'm happy to report that one is able to do this, and this is our theorem, that even in this setting, even against this monster, you can design a protocol for 1 of 2 OT, which is secure against general arbitrary devices, assuming the BQSM model. This is our result. And the key to this is something called the parallel repetition theorem. So we leveraged the power of the parallel repetition theorem to prove what we did, and we had to prove a new version of the parallel repetition theorem for the BQSM model specifically. But yeah, essentially this we showed that even in this completely screwed up setup, you can have completely device independent protocols. And in fact, this problem was open for a very long time. Believe it or not, the state of the art was that people only knew how to go up till IID. Like each device is the same. So like
you mean for BQSM?
For
under the BQSM
yeah.
assumption.
Yeah, under the BQSM assumption, IID was state of the art for a very long time. There was some like mild progress in the sense like people would do semi-device independent stuff, like okay, assume you can trust the state, but maybe you don't trust the measurements. There's literature on this called MDI, measurement device independent. But and there are other approaches where you can like trust the measurements but not trust the states. In fact, like approaches by DFRSS kind of allow you to do that. But it always seemed like if you try to prove one, you have to give up the other, and it was not clear how to get the general result. But in our work, we essentially show the general result. Yeah. And I should mention that this was presented at it's a little bit of like shameless self promotion, but this was presented at QCrypt this year. So yeah, so that's pretty much all I had to say.